Hi, and welcome to SFU Math 232. This is the lecture for section 4.4, coordinates. So the most important thing about this is going to be that we're going to understand that when we give the coordinates for a vector, it is with respect to a certain basis. We've already been doing this. I'm just going to give a quick example of what I mean. We've been writing a vector in this manner like this. Here's the vector 1, 2. This actually means 1 times 1, 0 plus 2 times 0, 1. So that this right here, we haven't been thinking about it so much, but this vector 1, 2, these numbers, the 1 and the 2, are the coordinates with respect to these two basis vectors. And we do not need to use the standard basis vectors here. So then the idea will be, what are these numbers if we have different basis vectors? They'll still be the coordinates of the vector, but they'll be with respect to a different basis. I want you to think of this problem like we think of numbers. So for example, if we had the number 7, and I just wrote that number down, what we sort of are thinking is, there are little 7 little things on the ground like that. And what we're implicitly understanding when we write that down, that is, this is 7 with respect to the base 10. We generally don't put that there because we're normally operating in base 10. However, we don't always have to operate in base 10, and we could represent this number of pebbles in a different basis. So we could, for example, represent it in base 2, which 7 in base 2 would look like this: 1, 1, 1, base 2. And this would be the same number of pebbles. It's not like the number of pebbles has changed, but we're now identifying the number with respect to a different basis. And we're going to do the same thing here with the vectors. Okay, so the coordinates of a vector are how much of each basis vector you are using. So now we have here a vector. There it is, 0, 3. And without further identification, we understand that to be with respect to the standard basis. And now what we want to do is represent that vector with respect to two different basis vectors. That would be v1, 2, 1 and v2, 1, 2. So what this means is we want to represent v as a linear combination of the two basis vectors. So some amount of v1 and some amount of v2. So that is going to be then 0, 3 will be equal to c1 times v1. v1 is 2, 1 plus c2 times v2. v2 is minus 1, 1. We want to find c1 and c2. This is simply two linear equations and two unknowns. The first linear equation being 2c1 minus c2 is equal to 0. The second linear equation, I'm reading now from the second row, c1 plus c2 is equal to 3. You solve that, two equations, two unknowns. We've done this a large number of times, and we find out that c1 is 1 and c2 is 2. So we would say we've got a basis B consisting of those two basis vectors. So we would now write that this vector, the vector v, with respect to the basis B, that's that guy right there, with respect to the basis B is 1, 2. And what that means is v can be represented as 1 of the first basis vector, 2, 1, plus 2 of the second basis vector, minus 1, 1. So what we're thinking geometrically here is that our two basis vectors, we can draw them. Let's just do that. We've got one basis vector, v1, which is 2, 1. So we would go along here by 2 and then go. So there's v1. That's the first basis vector. And then the second basis vector is minus 1, 1. So that is right here. So we got two basis vectors like that. And now we're asking about what the coordinates of v are with respect to that basis. Well, that's this v here. We're trying to go to this location, 1, 2, 3. That is the vector 0, 3. The vector is not moving anywhere. It's always right there in space. But what we're now finding out is that in order to get to the end of that red arrow, what we need to do is go one time along this vector like that, and then we need to go 2 times along this vector, which we draw it like this, like that. And that's what it's telling us. Once along V1 and twice along V2, and we will end up at 0, 3. Okay, so there's a definition for us here. We have a basis. It'll have some number of basis vectors in it. It's ordered. Okay, it's ordered V1, V2. You don't want to change the ordering of them. We always write our standard basis vectors in this way. 1, 0, 0, 1. Okay, this being the x coordinate basis vector and this being the y coordinate basis vector. Okay, we don't switch them around. So it is an ordered basis. So we have a basis for a subspace of Rn, and then we take a vector in Rn and we write it as a linear combination of the vectors of the basis. And we call those scalars here. We call those scalars the coordinates of the vector v with respect to the basis. Okay, and we order it. Those scalars in the bracket notation there to indicate the vector w with respect to the basis b is this ordered list of scalars. And we use each one of these scalars, a1, we use that scalar multiplied by v1, and then we use the second scalar, a2, multiplied by v2, etc., until we're at the end. Okay, there it is. We can write it as a column vector. We often write it as a column vector, and sometimes we write it this way to save space. Okay, so that is the coordinate matrix for W with respect to B. Just a side note, you'll notice I called this a matrix when you might be thinking to yourself, hey, isn't that a vector? But what we're going to be sometimes thinking of as this vectors would be a 1 by n or an n by 1 matrix. So a 1 row a matrix or a 1 column matrix. We sometimes use the word vector for that, and sometimes we use the word matrix, sort of mostly depending on context. Okay, so let's try an example of this. We want to find the coordinates of the vector W, which is identified as 1, 2, 3. Okay, because there's no subscript here, we understand these coordinates to be with respect to the standard basis. Okay, now what we're doing is we have a new basis, V1, V2, V3, and there are the vectors there, and we're asking, what are the coordinates with respect to this new basis, which is not the standard basis? First thing to potentially should maybe run through your head when you're doing these kind of problems is, I mean, we're being told here it is a basis, but you want to be thinking to yourself, okay, do I have a basis? That means, do those vectors span the space, and are they linearly independent? So this must be a basis. These vectors must be linearly independent for this to work. Okay, so then the question here becomes, here's the vector 1, 2, 3, and we want to know how much of the first basis vector do we need, and how much of the second basis vector do we need, and how much of the third basis vector do we need. It's important to note that the point in space that we are talking about, 1, 2, 3, does not change. We are just making it that we are just finding how to get to that place in space via different basis vectors, but the actual point in space that we're moving to does not change. Okay, in order to do this, we now have 3 equations and 3 unknowns. So I'm going to, rather than writing out the equations like I did in the previous example, I'm just going to go directly to the matrix. If you don't see how to do that right away, just stop the video and say, okay, I'm going to write out the 3 equations and 3 unknowns and then form the augmented matrix. Okay, so here's what it looks like. 2, 0, 0, 0, 1, 1, 0, 1, minus 1, and then we want to get to the place in space 1, 2, 3 as indicated via the standard basis. Okay, so now this is when we solve this system, we find out what C1, C2, and C3 are. So I'm going to leave that to you to do the row operations, or you could use MATLAB to do that, the RREF command. and then you will get this row reduced echelon form. And then that allows you to immediately write out what the constants are. C1 is a half, C2 is 5 halves, and C3 is minus a half. Okay, so now I can write the vector W relative to the basis B as 1/2, 5 halves, minus 1/2. And this is the same vector as the vector W written with respect to the standard basis. Let me just put the standard basis here: 1, 0, 0, 0, 1, 0, 0, 0, 1. We've been using these ones without thinking of that there's any other ones from the beginning of the course. Just like you head out into grade school and you use base 10 for a large period of time, and then like, hey, you know what? We don't actually have to do everything in base 10. We can do it in a different base. It's the same thing. Okay, so I'm just going to call that S, and we already knew that that was 1, 2, 3. The important point here is that this is the same vector. It is just the coordinates are different because they are coordinates with respect to different bases. All right. This is a sort of a reiteration of the question statement I've just been saying. Find the coordinates. Find these coordinates with respect to the basis of the standard unit vectors. And these are clearly nice to work with. So the standard unit vectors in Rn, there are n of them. Okay, it's an n-dimensional space. You have to have n vectors in your basis. So here I will write these guys out. This is in Rn. Okay, and there will be n of them. It's n-dimensional space. Okay, so there's n vectors. Let me just say that there's n vectors. And we call the first basis vector E1. We call the second one E2, etc., until we get to the end, the last basis vector, En, the standard basis vectors. And then W is simply these coordinates, because we are using those like this. We are using the standard basis vectors implicitly. So, I mean, these numbers will be exactly the same here. If I wrote, okay, here's W with respect to S, where I've indicated that S, this set here, is a set of standard basis vectors in Rn, these numbers will be identical. That looks like that. This is what we've been doing all along. We call it the standard coordinates of the vector. Again, just to sort of draw your attention to something that you've seen before, this is just like saying 4 and not putting anything here at all. And then we assume a base 10. So furthermore, anytime we see a vector, if there's no indication of a basis set, we'll assume that it's the standard basis set. If there is an indication of a basis set, then we will use whatever basis that is. So the question, the central sort of thing to learn for this actually quite short lecture is how to change from one basis to another. We've just done a couple of examples of how to change from the standard basis to a new basis, and we can change from one non-standard basis to another non-standard basis. So that's the key skill. So we have a vector in Rn, and we want to change from one basis, let's just call that B, to a second basis, B prime. I just want to know, I just want to note something that has come up. This means B prime means a new basis, a different basis. Okay, it is unfortunate that this B prime in MATLAB is the command for transpose. I do not mean the transpose of anything. Okay, we will always use, if we have a vector, we will always use the T like that, to, or for that matter, a matrix. We will use that superscript T to mean transpose. So just be careful of the context here. I know that has caused a bit of confusion. Okay, here we go. And then we're going to ask, how are the coordinate matrices, how are the coefficients that we use on the vectors related when we represent a vector in one basis and then we represent it in another one. Okay, so we're going to try to do this in the general case here. We're going to have two bases for R2. We're going to have basis B and we're going to have basis B prime. Okay, and what we're going to do is we are going to consider a vector with coordinates K1, K2 relative to basis B. And now what we're going to try to do is find what are the coordinates for that same vector W relative to basis B prime. So the method that we're going to use is we are going to take the vector V1 and we're going to consider what is V1 relative to basis B. Okay, so we're this guy here. V1 relative to basis V is 1 times V1, right? Plus 0 times V2. I mean, that is basically saying V1 equals V1. That is what it's saying. Okay, similarly, the vector V2 relative to its own basis is no amount of V1 plus the full amount of V2. So B1 in B prime looks like what? It is some two numbers, let's call them A and B. And V2, I'm talking about the basis vectors in B. How do I represent the basis vectors of B in the new basis B prime? So that is here, I'm going to call these two numbers, and I'm going to have to get this here, right? So we're talking about representing V2 in the basis B prime. And that is C and D. This means that the original vectors, V1, that this basis vector right here will be some amount. Now I'm going to try to figure out what those two numbers are. It's going to be some amount of V1 prime plus some other amount of V2 prime. And V2 will similarly be some amount of V1 prime and some amount of V2 prime. Sorry, some amount of V2. Next, I'm going to take a vector. I'm going to take a vector with respect to the original basis. So let's call that vector W. There's W with respect to B. It will have two coordinates, K1 and K2. This notation right here, means that W is equal to K1 V1 plus K2 V2. So now we're going to basically be doing a whole pile of substitution. So what is V1? K1, V1 is this guy right here. A V1 prime plus B V2 prime. Plus, now we're here, K V2. What is V2? V2 is this thing right here. C V1 plus D V2. Right. Okay, now I'm going to combine the coefficients on V1 prime together. So this is an algebra step here. So we end up with K1A from here plus K2C from here. And that is multiplied by V1 prime. And then we similarly end up with K1B plus K2D amount of V2 prime. So that means that the vector W with respect to the new basis is K1A plus K2C, and K1B plus K2D, which we can factor in this following manner: AB. I'm just going to make it obvious that I'm thinking of these columns as being important, multiplied by K1, K2. And that, in fact, is these numbers A, B, C, D. And what is K1, K2? That is W with respect to the basis B. So here we've got W with respect to the basis B prime is equal to these four numbers, A, C, B, D, multiplied by the coordinates of the vector W with respect to the basis B. Okay, this is the sort of general case. We're going to do a couple of examples, which is going to, I think, make it a little bit easier. Okay, so here, let's just have a statement of the change of basis problem, and then we will go through an example. So we have a vector. We have a vector in Rn. We have two different bases. We have an original basis, B. This is the original one. And we have a new basis, B prime. And we have a vector where we know the coordinates in the basis B. And now what we want to do is figure out what are the coordinates of that vector in B prime. So this is our equation that we're doing, that we're saying, what are the vectors? This is exactly what we did above in the R2 example. What are the vectors of W? What are the coordinates of the vectors of W with respect to B prime? It's going to be some matrix, which we call the change of basis matrix. And we then multiply that by the coordinates of the vector in the original basis. And here is how, this is what the columns of the change of basis matrix looks like. So we are changing from basis B to basis V prime. We form a matrix where the columns of the matrix are the basis vectors from the original basis represented with respect to the new basis. We call that the translation matrix, or the change of coordinates, or the change of basis matrix. All right, we have a small theorem here, in which we will just make use of. It is obvious, I think, and it's not hard to prove. But the theorem is telling us that if we do have two bases and we have a transition matrix going from B prime to B, and we have a transition matrix going from B to B prime, then those two matrices will be inverses of one another. Okay, this should be unsurprising. If you change from one basis to another, then you can change back. That's all it's telling you. You can go back. Okay. So let's figure out now in gory detail here how we compute this change of basis matrix. Definitely, this is something that you're going to be asked to do more than once. Okay, so we have two bases. Of course, we're being told they're bases, but coming into your head, should pop into your head as soon as you see that word. Oh, those vectors better be linearly independent. Okay, so in order to find the jth component of a vector, we'll take the jth component with respect to vector. Sorry, let's try that again. We will take the jth basis vector. Here, we're taking the jth guy from this set right there. We're taking the jth guy, and what we want to do, so we take that guy, and what we want to do is find out. We want to find this guy. We want to take the first basis vector from our original basis. We want to find out the coordinates of that vector in the new basis. That is, we want to figure out Vj, the jth basis vector of basis B. We want to express that as a linear combination of the basis vectors of B prime. A part of success in this program actually is to make sure that you are careful with your indexing. All the subscripts and superscripts need to be correct, otherwise disaster strikes. Okay, there we go. Okay, All right, we're going to let the vector x be the column vector of those coefficients. Okay, and so we then can identify Vj as V1 prime. That's the first column. This is a matrix I'm writing out, V2 prime, and these vertical bars are indicating the columns. And then we have the whole matrix, and then we are going to multiply it by this column vector right there, x. Okay, and so we now are thinking of that as a linear system, and we can then write the augmented matrix, and it looks like this, V1 prime, V2 prime, like that, a whole pile of columns, all up until Vn prime, and then it's augmented by the coordinates of Vj in the original basis. We use row reduction to row reduce this matrix right here. We row reduce this matrix until we have the identity matrix on the other side, and we then have here Vj B prime over here. Okay, and we need to do that for each one of these vectors that we have from the original basis. So what we're going to do is end up augmenting. We're going to end up augmenting all of these vectors with all of the vectors from the original basis. Okay, so this, we did it for one of them to sort of see why this works. And now we're going to do it for all of them at the same time. So here's the procedure, the algorithm that you should be able to execute. Okay, so you want to change, you want to find the matrix for changing the basis from basis B to basis B prime. Then here's what you do. You form a matrix. The columns of the matrix will be all of the vectors in B prime, and then all of the vectors in B. Okay, do it in the right order. B prime has to be first and B has to be second, and we are changing bases from B to B prime. That's the easiest mistake to make, is to put the columns in the wrong order. Okay, so caution when you're doing that. Okay, then what we do is we do our magic Gaussian elimination procedure, and we reduce the matrix from step one there to reduced. You have to go the full way. Okay, reduced row echelon form. There's going to be no back substitution in this model. The resulting matrix will be the identity matrix, and then there'll be a whole pile of columns here, and those columns will be what you want. That will be the matrix that changes vectors from basis B to basis B prime. You extract that and you write that down, and that is your that is the procedure. So I'm just going to put a little sort of mnemonic here to help remember that. Basically, you're putting in the new basis vectors here, new basis vectors here. You augment with the old basis vectors here, like that. And then you do the row operations, the Gaussian elimination. So row operations, and you do the full Gauss-Jordan elimination until you get here to the identity matrix. And then over here is the matrix you want. Okay, let's do an example of this. This is our final thing here to understand how to do this. So we are going to do a change of basis from an original basis to a new basis. And we're being told that our original basis is in fact E1, E2. And when you see E1, E2 like that, and there's no further illumination, you assume those to be the standard basis vectors. So our old basis that we're starting with, or original, if you want to look at it that way, our original basis vectors are E1, which is 1, 0, and E2, which is 0, 1. Our new basis that we want to go to, we've been given those vectors in the problem. That is V1, which is 2, 1, and V2, which is -1, 1. Okay, here's the procedure. You take the new basis vectors and they go into the matrix as columns. You take the old basis vectors and they go into the matrix as columns. And then you do the row operations that you need in order to turn this right here into the 2x2 identity matrix. So allow me to do that in one fell swoop using MATLAB. You can use MATLAB, or perhaps if you need a little bit more practice doing that by hand. You go do your row reduction until you get to this step right here. And then you have your matrix that you were looking for. We're going to label that P B to B prime is going to be this right here. 1/3, 1/3, minus 1/3, and 2/3. Now, we can now use that to change any vector that we're given in basis B and find the coordinates for that vector in the basis B prime simply by taking this matrix and multiplying it by that vector. Let's just end this lecture by doing that procedure for one vector. We imagine we get a vector V relative to basis B. And let's just say that vector looks like this, 1, 1. Now what we want to know is, what is that vector relative to basis B prime? What are the coordinates of that vector V relative to the new basis? We simply take our, well, I'll write it out as a formula first, and then I'll do the numbers. What we're trying to do is find this, and it is the matrix P B to B prime multiplied by that vector there. And that looks like this. So we're trying to find the coordinates relative to the new basis. We take the change of basis matrix that we've found. It's that guy right there. And we multiply it by the coordinates relative to the original basis. And we get two numbers, these numbers here. Okay, that is, I can then write out the vector V relative to B prime is 2/3, 1/3. Okay, so we have a clear algorithmic procedure to develop a matrix that allows us to find the coordinates of a vector where we know the coordinates in one basis and then immediately find the coordinates in a with respect to another basis. And that is all for section 4.4. Thanks, guys. Bye.